Okay, so one thing that's I was pointing out yesterday about limits approaching infinity and negative infinity, especially if the degrees are the same, is that we don't care which side is going. As if the degrees are the same, we just take the ratio of the coefficients, right? We don't do a negative 5/2 and the 5/2. We just do whatever the ratio is, right? If it gives us 5/2, then we just keep it. Because most graphs, rational functions at least, if there's an asymptote, it's going to be the same asymptote whether we're going left or whether we're going right. Okay, it's going to be that same. Okay. Now, I want us to establish that this is the most common type, but because AP exam does test this other type of function, I want to go over it, but I want to kind of help you understand that, I mean, it's going to be on the test, but it's also very, it's less frequent. Okay, it's like an exception. Okay, so what we're learning today is kind of like an exception to the rule, but it is something that has shown up before, so I want to make sure I go over it. These are horizontal asymptotes with radicals in the denominator, maybe sometimes even radicals in the numerator. But you see how this function looks a little bit different. It's not your rational function where you can, without, basically, if there's a radical in it, you know that there's something a little strange about the graph. And here's what's strange about the graph. You see how this is what the graph looks like. Towards 1, if we exit the graph, or if we follow the graph to the right, it is heading out at a 1 horizontal asymptote. But if we go in the other direction, it's going to another horizontal asymptote. Okay, so most graphs don't look like this. Okay, the graphs that we work with mainly look more like this. There's a rational function, there's an asymptote, and it's going to be the same asymptote on both sides. Yeah.
How's the line able to cross that asymptote though? Like the bottom one.
Right. So we talked about how the horizontal asymptote, it doesn't restrict the graph from crossing it. It only tells us how it's behaving near the end.
Okay.
Right. So if it's a vertical asymptote, then that is true. We can never cross a vertical asymptote, but the horizontal asymptote doesn't prevent the graph from crossing it. It just tells us how it's looking towards the end. Okay. Okay. So how do we determine what the horizontal asymptotes are when we don't have the graph in front of us? Okay. So so anytime we're asking about horizontal asymptotes, we know that we're asking about limit as x approaches infinity. So I want you guys to equate those two things. Horizontal asymptotes is equivalent to limit as x approaches infinity. So let's do approaching infinity, the positive version at least, for 3x minus 2 over the square root of 4x squared plus 5. Now, this is a little bit different, but we know that if we're doing infinity, we're comparing degrees. Okay. Well, what is the degree of the numerator? 1. Okay, good. What is the degree of the denominator? Also 1. Now there's the x squared here, so why is it 1 and not? And why is it 1 and not 2? The square root, right? The square root ultimately is going to transform that x squared back down to an x. So, okay, so we see that, right? That there is the degree are the same because the square root is going to undo that x squared. Okay, so we're going to do what we've done in the past. We're just going to take the ratio of the coefficients because the degrees are the same. What's the coefficient of the top? Okay, what's the coefficient of the denominator? Good. Yeah, good, 2, because that square root of 4 is going to undo that. It's going to convert it back to a 2. Okay, we don't care about anything that has a lower degree. It's just going to fall by the wayside. We're just going to focus on the highest degree here. Okay, so good. So square root of 4 is 2. That is 1 horizontal asymptote. Y is equal to 3/2. And we can kind of see that it's consistent with our graph. We're not going to sketch the graph, but I want to kind of show you that what we're getting does match the graph to be true. Okay, y equals 3/2. Okay, you guys see that? All right, now let's look at x approaching negative infinity. Okay, same function. We are in agreement that the degrees are the same. All right, degrees are the same. And we're still going to do ratio of the coefficients. We're still going to do 3/2. but there may be a slight change here, okay? Now imagine inserting a large negative number in for x. What's going to happen to the numerator? Negative, okay, so that's negative, okay. Now, if I inserted a large negative number in for this x here, what's going to happen? It's going to stay positive because negative 100, negative 1,000, negative 1,000,000 squared is going to be positive, and the square root of a positive is positive. So this is negative over a positive. That is going to cause the sign to change. So there's a different horizontal asymptote. But the good news is that it's sharing the same ratio. We're just changing the sign. So one side is headed towards 3/2. The other side is headed towards negative 3/2. This is only going to happen when you're dealing with these weird looking functions with the square root. Okay. Otherwise, it's going to be the same asymptote on both sides. And this is the only time that we're going to have split asymptotes. If you see a radical in the denominator and the degrees are the same. Okay.
Yeah, how do you get like 3/2 for like what number do you plug in for it?
Oh, well, we know that the degrees are the same. We're just taking the ratio of the coefficients. All right, so what's in front of this x?
Oh,
3,
3.
right? And what's in front of this x squared?
Square
Square root of 4, which is 2.
These are both completely the same. Because the 2's under the square root. Degrees both the same.
Yeah, exactly, right. The degrees looks different initially, but they're actually the same because the x squared is under the square root, right? Okay, so that's the only example that I want to go over. You're going to see it in your homework, and we're going to go over it in our test review. But any questions about that? Yeah.
And why is it negative 3/2 for the?
Right. The reason why it's negative 3/2, because imagine if I'm plugging in like a negative 100 into x, what's going to happen to the numerator here?
Numerators become negative.
Negative. Okay, but if I insert negative 100 into this x, what's going to happen?
Be positive.
Stay positive because it's negative 100 squared, which will turn positive. So negative over a positive is going to be negative. But the big picture is that whenever you see this and you find the ratio of 1, you know that there's also going to be a negative version of that ratio because of that split asymptote. But this is the exception to the rule. Okay, most, I mean, we don't even know if it's going to show up on the AP exam, but it has shown it before. So I want to make sure I go over this kind of exception.
It'll be on the test.
Yeah, it'll be on the test. Yeah, but you can spot it easily, right? Radical in the denominator, degrees are the same. You're expecting 2 asymptotes.
You only define like the 2 y values. So.
Yeah. So we have our 2 lines here. Y equals 3/2, which is up here, and y equals negative 3/2, which is down here. Yeah.
I'm gonna have to like draw it.
No, you just have to be able to name it. Yeah. Okay. Any questions with that? Okay, so now the last thing is going over something called comparative growth rates. Okay. Comparative growth rates is only going to work for very specific situations, but it's going to be very helpful when we talk about curve sketching and further on. It's going to be a nice relationship for us to find values that are limits that feel very difficult. So here's the big set of notes here, or the big key thing here. Families of functions grow at predictable rates in relation to each other as x approaches infinity. So that's something to keep in mind, that this only works if we're approaching infinity. Okay. So, as we move to the left of the graph, the relationship breaks down, but the relationship is going to hold if we move to the right. So here, I want to show you that these are the 4 families of functions we're going to work with. You got logarithms, which is like natural log of x, log base a of x, log base 2 of x. Okay, anything that is but the most common log function we're going to use is natural log. Okay. Logs grows at the slowest rate. Okay, so you can see that it's rising, but it's not rising very fast. Okay. Next up are radicals, like square root, cube root, fourth root, but square root is going to be the one that we see the most often. You can see square root kind of has a similar shaping as the natural log, but it's going to grow a little faster. Okay, a little faster than natural log. Next up, polynomial, algebraic, anything like x squared, x cubed, any thing like that. For instance, x squared, grows at, you can tell, is a much faster rate than either of these two, right? So x squared, x cubed, I'm just going to give an example here as a polynomial. And finally, exponential. Exponential, it's like e to the x, 2 to the x. If your variable is in the exponent, we call that an exponential function. So 2 to the x, e to the x. E to the x is going to be the one that we see the most often, but exponentials can also be other constants raised to a variable. So this is exponential function here.
Well, x cubed like go to power squared and x squared though.
It will, right? But we're only going to be comparing between different families of functions. If it's x cubed over x squared, we can figure out by comparing degrees. But if we're comparing different families of functions, there's going to be a nice relationship here because they're going to be predictable as we go towards infinity. Okay, may not be initially, but if we go towards infinity, they're all going to settle into these nicely defined relationships. So this is what I want to show you. There's two scenarios here. Let's say I have limit as x approaches infinity. Let's say a slower function is up top, but then the faster function is below. What's going to happen to that limit? Approach 0. Yeah, that's it. So if the slower function sits above and the faster function sits below, it's always going to be equal to 0.
Wait, why so?
Because if you imagine your denominator getting faster than your numerator, what's going to happen to that fraction?
It's going to keep getting
smaller and smaller, and it's eventually going to head towards 0. Right. Here's the other scenario: the limit as x approaches infinity. What if the faster growing function is up top, but the slower function is below? Okay, good. Positive infinity or what?
Or negative infinity?
Or negative infinity. Yeah, it's going to go in one of the directions, right? It's either positive or negative infinity. And guess what we can do to test between these two options? Okay, we can test what number would be a good test. Yeah, so similar to if degree is higher than the denominator, we'll test 100. And then whatever, if it's positive, we know it's this. If it's negative, we know it's this. Why would we never have to worry about testing x equals negative 100?
Because that's negative or excuse me.
Why do we never have to worry about going left?
Because I was approaching.
So the reason is because this, especially if we're dealing with this comparative growth rate, this is only going to hold for infinity. So if it's going towards infinity, we're going to have to do something else, and we're not going to have to. We're not going to be able to use this test. So this test only works for infinity. So that's why we never have to worry about testing going left. But the y value can either go up or down. Okay.
Why does it only work for infinity?
Because if you look at the graph here, right, e to the x, x squared, natural log of x, square root of x, it doesn't have that relationship on this left side, right? We don't see logs existing here or radicals existing here. And x squared is higher than e to the x, so everything is off on the negative side. It's only true for the positive side. All right, so let's look at example 1. Okay, limit as x approaches infinity. You can see that the numerator falls under one category of functions. Oh, and also, if there are different pairs of functions, like those like radical x plus 2 to the x all over natural log of x plus polynomial, if there's different families of functions mixed between numerator and denominator, we're not going to be able to know which one is growing faster or slower. And you're not going to be asked that question. It'll be, if you're asked about this question, it'll be very clear. Numerator is one family of function. Denominator is clearly another family of function, and it's approaching infinity. So look at the, this looks complicated here, but
That'd be 0.
okay, what's the family of function for the numerator here?
Square root of x.
Yeah, so it falls under
Slower category. Oh,
radical. Okay. And then the denominator is polynomial, algebraic. Okay. So which one is growing faster?
Bottom.
Bottom. Therefore, limit is 0. So comparative growth rates allows us to gain a quick view of what the limit is without doing a lot of work, because we know what the relationship is between the functions. Okay, 13 looks messy, but approaching infinity, the numerator falls under which category?
Logarithms.
Logs, yeah. Denominator falls under
Polynomial.
polynomial algebraic. I know it's not degree 2, but we still call it algebraic in that algebraic polynomial category. Okay, which is growing at a faster rate. Bottom, therefore, still
So zero.
0. Okay. All right, number 12. Again, approaching infinity. Numerator falls under what category?
Exponential.
Exponential. Denominator falls under
Polynomial.
polynomial. So, which is growing at a faster rate?
That's
Top. Therefore, where's it going to go?
100. Okay.
Yeah, it's either positive or negative infinity, right? It's one of those directions. So we'll test 100. What does numerator give us?
Positive, right?
Well, e to the 200 is positive, but there's a what in front?
It's a negative.
A negative. So it's negative over. Denominator will give us a positive. So negative over positive is negative. Yeah.
Why wouldn't that like negative distribute to the e first before it was like?
Well, there's only one term here.
So it wouldn't be like negative e times like it wouldn't be.
So it ends up being negative e times 2. So, okay, yeah. So exponential always, when we do order of operations, we always take care of the exponent before the multiplication. So e to the 200 is a positive number. That times a negative 1 is going to be a negative number. Does that make sense?
Yeah.
Yeah. Okay.
I was gonna say it's like it's an even exponent, so it usually would cancel out the negative.
Because like
Yeah, that's only if it was e to the, let's say if it was like negative x squared, right? Then, negative 100 would be canceled out by the 2, and then that will stay positive, right? But this is, imagine this is saying negative 1 times e to the 200, right? That's what this is saying, right? So e to the 200 is a positive. Positive times negative 1 is going to be negative. Okay. All right. Okay. All right. Example 14. Okay, we see clearly defined families between numerator and denominator. The numerator falls under what? Radical. Denominator is logs. Okay, which is growing at a faster rate. Top, so we know it's either positive or negative infinity. Let's test 100, because that's where we're headed. So numerator gives us negative, yeah. Denominator gives us positive. Negative or positive is negative. So hopefully you find this pretty easy. I think the only thing you have to make sure you know is the relationship, right? Make sure you know logs is slowest, radicals, polynomials, exponentials. And so maybe something that will help is that that these fall in, yeah, sorry, that that polynomial and exponential are, I think students tend to have an easier time with this. Exponential is the fastest, polynomial is next. They sometimes get the logs and radicals mixed up. So just think alphabetical order, logs before radicals.
You got to the bottom.
Yeah, good. All right, everybody okay so far? Okay.
There's a lot of topics from this unit.
That's right. These are all the topics in the unit. Let's go to the test review, and let me point out a few things before we jump into all of it. Okay, there's a couple of reviews in here. We're gonna see if we can step through review number 1 today. If we don't finish, it's okay. We can pick that up on Monday. And then on page 5, there's test review worksheet 2. We'll tackle that on Monday and Tuesday. On page 9, these are some important steps for our important concepts. I'm going to spend some time going over that in a second. We don't have a quiz. In the past, I would have 2 quizzes before the test, but there's no quiz here. But I think this is still good review, so I put the reviews in here that if we have time, we can go over on Tuesday. And then I also have a morning review. I'll go over this morning review on the day of the test in the morning. Obviously, you can encourage you guys to work through beforehand, but want to make sure that that you guys knew what my plan was. Okay, and finally, well, let me start off with this here. Here are the test topics, and want to make sure that you knew exactly what was coming up. So evaluating limits algebraically, real numbers approaching infinity, one-side limits. So these will be mixed, and we'll see that on the first page of our test review. And we've been working with this the most. So being able to understand the steps, right? If it's approaching real number, you always do direct substitution. If it's infinity, you know you compare degrees. Evaluating limits with algebraically with holes in the graph. So this is what showed up on the quiz, factoring, conjugates, common denominator. So make sure that we review through our quiz. Identifying limits and order pairs from a graph. We did that on the quiz. Sketch a function graph given limit properties. You did that on the quiz as well. Use continuity conditions with piecewise to determine continuity, discontinuity. We spent a day on that, so we'll come back to that in our review. Apply IVT, intermediate value theorem, to guarantee a value. We worked on that. Horizontal asymptotes, we just did that today, right? We know there's a split asymptote. We know there's going to be, in this. Okay, so let me ask you this: what are the 2 asymptotes that's going to show up here? Say it again. Yeah, right. So my degrees are the same, right? Because the x squared is under the x, it's under the square root. So we have y is equal to 3 over root 5, and we know going in the other direction, there's also a 3 over a negative root 5.
What happens to the x squared minus 4 at the bottom?
Yeah, we don't care about the -4. Anything that's a lower degree doesn't matter, right? Just like before, when we talked about comparing degrees, we only care about the highest degree because lower degree is not going to impact the behavior of the graph.
You take the x's out too.
Right, we just take the ratio of the coefficient because x and x squared are the same degree because the square root. So we just take the ratio of the coefficients, which is 3 over root 5. Right. If I clean this up, it's really 3x divided by root 5x. Right. The degrees are the same, so I just take the ratio of the coefficients. But it's radical, so I know there's a split asymptote. And then you'll see a comparative growth rate like this. So let's do this one here. Okay. What does the numerator fall under?
Exponential.
Exponential. Denominator falls under
Radical.
radical. Therefore, it's going to be either
Positive.
positive or negative infinity. You test 100 in for the x. Numerator, we get
Positive.
positive. Denominator, we get
Positive.
positive. Therefore, positive. Okay, so any questions with test topics?
How long is it going to be? This?
3.5 pages. Yeah.
Good old class student.
Yeah, whole class period. Okay. Any other questions? Okay. All right. So let's go to. Let me do the highlighting the steps here. So page 9. Okay. So we talked about how there are two main categories, right? If you see approaching a real number, you're doing direct substitution, right? Plug in that argument x value. If you see infinity, you're comparing degrees, right? See which one had a higher degree, and then just, go through that process. So first step, we always plug in the x value. We ignore the one-side limit, and then we try to find the limit. Okay. If we can get a real number, then great. If we get 0 over 0, we're going to reevaluate. We know we have to go through our steps to get that hole to be removed. If the limit does not exist, right, 10 over 0, 8 over 0, then we will say that's fine, limit doesn't exist. But if there's a one-side limit paired with a limit doesn't exist, we know we gotta involve decimals, right? We gotta plug in decimals. Okay, so that's the hard part here, is knowing when to involve decimals and when to ignore the one-side limit. Okay. All right, and then if we're approaching infinity, we know that we're comparing degrees. If my denominator is higher than my numerator, I know my limit is going to go to 0. If my numerator and denominator are the same, ratio of the coefficients, if my numerator is higher, then it's going to be plus or minus infinity, and I would test either 100 or negative 100, depending on where my graph is headed. Okay, I'll come back and review the continuity conditions once we get past these limit problems. So let's go back to page 1, and then the keys are all attached. So if you're working ahead, then feel free to check your answers. Okay. All right, so the additional complexity that is going to come from these problems is we're going to have to read the piecewise function to determine which expression is appropriate for the limit that we're finding. Okay, so I'm going to put on a separate sheet just so I can have more room here. So part A, we're on page 1. So part A says limit as x approaches negative infinity of g of x. Now, negative infinity, and we want to choose the appropriate expression here. So x plus 4 is used if we're greater than 5. We'll use between 2 and 5 if it's we use 2x minus 1 if our limit is between 2 and 5, and we'll use x plus 5 if our limit is less than 2. Okay, and here's something that is going to throw students off, is that what are these here? These are simply what? Points, and points have no say as to the limit. Okay, so if you're looking at a limit, do not look at the point. The point is there to distract you. Okay, it's not going to impact your limit at all. You're going to only look at what is in a range of graph, because you want to look at connected parts of graph, not single dots, not single points. Okay, so limit as x approaches negative infinity, which expression will live if we continue towards negative infinity?
X plus 5.
X plus 5. Okay, so that's less than 2. Okay, so x plus 5. Now, if we see negative infinity, what do? We compare degrees, right? But I know you don't see a degree in the denominator, but we can always put what in the denominator if we don't see it? A 1, right? So what's the degree of the numerator? 1. What's the degree of the denominator? 0. Which has higher degree? The top, right? So it's either going what? Positive or negative infinity. Okay, so we test with a negative 100. Numerator, we get negative. Denominator is 1, so that stays positive. So negative over positive is negative infinity.
I didn't know it was x plus 5.
Because we're approaching negative infinity, and negative infinity, imagine a number like negative 5, negative 10, negative 20, negative 30. Those are all values less than 2.
Okay. Yeah. So it says something like less than, and it's approaching negative.
Yeah, yeah, depending on your interval here, right? This x plus 5 is going to live between negative infinity and 2. All right, part B. Okay, 2 from the left side of 2. So imagine numbers like 1.8, 1.7, 1.6. Where are those numbers going to live? Which expression? Is it the x plus 5 or the 2x minus 1? Oh, right now we're just picking which expression to use. Okay, so
Why is X so 5?
it's x plus 5, right? Because we're coming from the left side of 2, and
So right.
x is less than 2, that is still, right? So from the 2 from the left side of 2 is still less than 2, right? So x plus 5. All right, so if we see a one-side limit, algebraically, we don't do anything with decimals, right? What's the first step that we do? Plug it in and we get 7. Yeah. I know the temptation is you want to do decimals because you see that one-side limit, but we only do one-side limit if we do direct substitution and then realize there's a vertical asymptote. Part C. Limit as x approaches 2 from the right side of 2. Which do we choose for
That'd be
that?
2x minus 1.
That would be 2x minus 1, okay? Because to the right of 2 is over here, right? Between 2 and 5, those are values to the right of 2. All right, first things first.
Degree.
Part D.
Should be 11.
That's the temptation, right? Is that we want to look at that 11, but that's the point. We never are caring about the point if we're now if it was asking for g of 2, that's perfect. G of 2 would be 11, but the limit, that's just the point here. We want to look at the connection from both sides. So, what did you guys say? Okay, y does not exist.
Plus.
Okay, and y is a non-removable. Good. So you see how does B, you see how B and C supports D here? Approaching 2 from the left is going towards 7. Approaching 2 from the right is approaching 3. So there's a disconnect. Jump discontinuity. So therefore limit does not exist.
I have to explain.
No, you just have to say it doesn't exist. Okay, approaching 5 from the left. Which one do we use here? 2x minus 1, okay. Direct substitution, always the first step. 9, okay.5 from the right. 5 from the right.
X plus 4.
Good, x plus 4.
That's also
9, also 9.
So the one that does 6.
Let's look at part G here. Limit as x approaches 5 of g of x.
Is 9.
It's 9. Now, even though it's trying to distract you with that 20 is not telling us what the limit is. That's just the point. The approach, though, is consistent. See that how E and F is supporting G. The left is approaching 9, the right is approaching 9. Even though the point is living elsewhere, there may be a hole there, but it's okay because the approach is consistent.
What would be the reasoning behind that? What would be the reason that's then?
Right, so the reasoning is because anytime if the limit as x approaches 5 from the left is equal to the limit as x approaches 5 from the right, if they're the same, then the true limit exists, right? Remember how the very first day we did limits, we used arrows, right? The arrows are pointing to the same y value, then our limit exists. So that's the notation under continuity conditions for that.
You don't have to explain on the test, you said.
Not for this section, but later on, if it's a continuity condition problem, I do want you to show your work or show your notations, your justification. Part H. Approaching 6 from the right.
It could be x plus 4, we're not sure, no, this can be less than 6.
Well, for everything greater than 5, we're going to use x plus 4.
Okay.
So it'll be x plus 4, right? Because 6 is obviously to the right of 5. So this is the only option that we have. This is where the graph lives. What do we get?
Then F.
Okay, limit as x approaches infinity. X plus 4, yeah.
Where's like when it's like infinity or negative infinity?
Yeah, good question, right? So if it's infinity or infinity, we do what?
But over 1.
Compare what? Compare degrees, right? So if you don't see any degree in the denominator, you can just always force a 1 there. There's understood 1 there, okay? So now we compare degrees, which has a higher degree? Numerator, right? This is x to the first power. This is x to the 0 power. Numerator wins out. So if my numerator has higher degree, what are the options? It's either positive or negative infinity. So then you would test 100.
Positive.
It's positive. Positive over positive is positive, so therefore positive.
You said it's like, if the limit is approaching positive or negative infinity, then you compare
Compare degrees.
degrees.
Yeah. Okay, so I want you to get a taste of what it's like on Monday. We're going to do a problem that's a little bit more involved. So, but at least we kind of know how to pick the expression based off of the piecewise, restrictions, right? Okay, let me review continuity conditions and then let's try number 2. So again, page 9 here. Right, so we want to make sure that we memorize our continuity conditions. Okay, so the condition is the point defined? Second, does a limit exist? You'll just evaluate the limit. But if you see a less than, greater than, and 2 different expressions are involved, you got to do one side limit. You got to evaluate the limit from one side of that x for an expression and limit as it approaches c from the other side from the expression and see if they agree. If they agree, then you can conclude that limit exists. And if we only go to the third condition if we realize that the second condition passes, right? Because if the second condition fails, we know it's going to be a non-removable discontinuity. If the third condition fails, we say that it is a removable discontinuity. And obviously, if the third condition passes, then that means we pass 1, 2, and 3. That means the function is continuous at that point. Okay. All right, use continuity conditions to justify whether the function is continuous or discontinuous. If discontinuous, identify the type of discontinuity. So what is the point that we are focused on that we care about here? 3, yeah, we know that 3 is where the potential issue could be, and we're trying to determine if there's an issue at 3. Okay, so first things first, order pair, f of 3. F of 3 corresponds to which one? First or second? First, because there's an equal sign there. what does that give us? 14, okay, so we keep going. Second condition, does the limit exist? Can we rely on one limit statement or do we need two? We need two, right? Greater than has an expression, less than has different expressions, so the left and right are going to involve different expressions here. So limit as x approaches 3 from the left side of 3. Which one do we use for left side of 3?
Square minus 2.
X squared minus 2, okay. Gonna leave some space here and do the other one. So from the right side of 3, we're going to use x squared plus 5. Okay, we're going to evaluate them both. What do we get here? Here we're going to get 14. Okay. What can we conclude?
But discontinuous.
Discontinuous because why?
There's jump past.
Jump discontinuity. Okay, but what notation am I looking for you to show me?
That's just the left side is not.
Okay, okay, so pay attention to the notation here. We're going to say that the limit as x approaches 3 of f of x does not exist, and our reasoning is we don't want to, I mean, obviously 7 doesn't equal to 14, but what I want you to say is limit as x approaches 3 from the left of f of x does not equal to the limit as x approaches 3 from the right of f of x. Okay. That's what I'm looking for. And again, this is what I see a lot of students do. Why is this not, why is that incomplete?
So to say it does not exist.
Yeah, I want you to be able to show me what expression you're talking about. Okay, I know this is how we say it, but this is the way that we write it. Okay.
The whole thing is the answer like that.
Almost. It says if discontinuous, identify the type of discontinuity.
Jump.
Another word for that, non-removable.
Okay.
Okay, is it non-removable everywhere?
No.
Okay, so I want you to specify what point you're referring to. Okay, so I'm going to be picky about the notation, but that is what they're looking for in AP exams. So I want you to show me all these things. So if you take any shortcuts, if you abbreviate things, and I may know what you mean, but I'm looking for these wordings.
You don't do step 3 for that problem?
Right, why do we not do step 3?
Because they're not even.
Because, yeah, because we already know what type of discontinuity, right? We only look at step 3 if we realize that there is a chance for a removal discontinuity. Okay, good. We're gonna pick up where we left off. You guys do have homework still over the last part of 1.5. I'll send out a reminder this weekend. Come get your phones.
Thank you.
Thanks, Zach.
We go for that first portion where you define the limits of all those equations. Did we do that at the very beginning? You didn't? Been a while. Like the first portion we did.
What do you mean first portion?
Like the one like the A for H.
Like these types?
Oh, no. Like the first part in the test review that we did today, like yeah, that part.
Oh, this part here, yeah.
Yeah, did we do that at the very beginning?
No, so this is kind of like a new
Yeah, I remember
variation.
doing that. I was like,
Yeah.
So it's like a new, it's like a new variation, new version.
New variation of what we already know how to do.
Mr. Joe, you talking about as well?
Okay.
Yeah, it is. So you don't have to worry about like cotangent, like unit circle stuff.
Yeah, no trig, yes.
Okay.
We'll do trig near the end of the semester.
Okay. So we're gonna have to do it eventually. For like
Eventually, yeah.